Yeah, if you go to the course web page and you look at the reading, this one, yep, 6-1. So right here. So the question was in the lab, the table number was wrong. So it's not table 5.5, it's table 6.1. But that's from last week's lab. It's this table right here from the reading. All right. Oops. Okay, so on the syllabus this week is marked as a continuation of last week. There was like 100 and something slides. So we're going to finish off talking about Kriging, and then I'll try to bring up ArcGIS and kind of demonstrate the geostatistical analysis for doing Kriging. So you can do Kriging through the toolbox that we did last week, but the geostatistical analysis allows you to apply and really probably helps you to learn a little bit about what we're going to work through. So if you download the lecture, or you probably already have it downloaded on your computer, and we'll start. What will happen? I forgot exactly what slide I got to, but we did start talking about Kriging, and I'll breeze through these first few slides until we catch up here. But we started talking about Kriging, and we started to mention that Kriging basically has two elements that we're concerned with, and we're actually, the first one that's listed there is not always of concern. Okay, the first one that's listed there is trend. So Kriging does consider a trend if you choose to let it consider the fact that there's a trend in your data. In other words, if you're talking about elevation and you've got a slowly descending elevation slope in the area that you're trying to interpolate, or perhaps maybe even a more realistic scenario, if we're talking about some sort of pollution or something like that, and there's some distance decay associated with that. As you move further away from some point, just in general, there's less and less of the element that you're trying to interpolate. In that case, you can tell it, hey, there's a trend in my data, and Kriging will take that into account. Just turn it down my phone here. And that's one of the powerful aspects of Kriging that IDW doesn't. I'm going to compare Kriging a lot to IDW because it is similar in the way that it utilizes weights. All right, so the second element there, that element of variability, that is in every Kriging method that we'll talk about today. And specifically looking at quantifying the spatial autocorrelation in order to determine the weights. The spatial autocorrelation means how closely are nearby points related to each other. And then the random variability will actually play into how well we can say with confidence that our predictions are accurate. So how certain we are that our predictions are what we predicted. Okay, so I think we did already do that slide. And this slide, we talked about how Kriging is similar to IDW. Here, right here, we're still talking about assigning a weight to a point. Okay, multiplying them up and summing them all up, all the neighboring points to determine the value at an unknown location. So when I say an unknown location in interpolation, what I'm talking about is the center of every grid cell. Those are the unknown locations that we want to interpolate. There could be cases where we were trying to interpolate a specific location, and that was really the only location we cared about. And that would still be spatial interpolation. But most of the time, what we're talking about here is building an entirely new raster data set. And so we have an evenly spaced grid cells, set of grid cells, and we're trying to find out what the unknown value is at the center point of every location. That's what the inputs are going to be, a bunch of points and a grid, an evenly spaced grid that you're going to define the parameters, the extent and the cell size. Those are the inputs. The outputs to this process are always a grid that's the same size as that input grid, where it's been filled in with every with the value at the center point of every cell. So in Kriging, the weight depends solely on the distance to prediction. Sorry, in IDW. In Kriging, however, the weights are based on the overall spatial arrangement of the points. We use math, or the computer uses math, to come up with different weights depending on the data itself. So you don't come up with the weights. Okay, so we did talk about this, uncover the dependency rules and make the predictions. Those are what is necessary for the Kriging process. And in order to come up with these dependency rules, we need to examine the degree of spatial autocorrelation. And to do that, the first step is what we call creating we say semi-variogram in Kriging. Okay, semi-variogram and a variogram are very similar, but we're talking about examining the variance. Okay. So this would be like a cross section of some data. This might represent elevation data, and these are the points, the known point locations. Okay. The trend would be this line right through here. The trend surface is a surface that we fit through the data that tries to minimize the distance from all of these points back to the trend surface. Okay. Autocorrelation is the degree to which nearby points are related. So in this case, as distance increases, we would expect to see nearby points be less and less related to each other. Okay? There's more variability. Another way to say that is that there's more variability in points that are further away from each other than points that are close. In other words, let's say we took any given point, and that we know that what its value is, and its value is x. If we sampled points that were 100 meters away from x, and we looked at how different they were from x, one way to quantify that would be to come up with a variance. How do we calculate the variance? Well, we take all of those values, we add them up, and we divide by the number of values. That gives us the mean. Okay, so we got the mean. To get the variance, what we do is we subtract each of the individual values from the mean, square those differences, add all those differences up, and then divide by the total number again, because we're adding them all up. So we're basically getting the sum of the squared differences from the mean. So if we took 10 points that were about 100 meters away, and we took 10 points that were 5 meters away, you would expect that those points that were 5 meters away would have a lower variance. In other words, they'd be more similar than values that were 100 meters away. That's what this chart is trying to show you. Okay. And correlation, I framed it in terms of variance because that's actually the way that Kriging does it. Variance and correlation would be inversely related. So if you can imagine this said distance, but this said variance, the chart would be like going like this, where it would be going up. As distance increases, you'd expect variance to go up. All right, so yeah, here's a mathematical formula that expresses that. We say semivariance because what we're talking about is dividing this variance value. So this is the average variance when comparing a particular value to a value far away from it and squaring that difference. Remember I said to square the difference. We're going to take the average. So the average of what? Well, in this case, what we might do to look at the semivariogram was take the average of all the values that were 100 meters away, and the average of all the values that were 90 meters away, and the average of all the values that were 70 meters away and 60 meters away, and so on. Every 10 meters, we take the average difference between the known location and all the other values that are X meters away, square them, and then we take half of that to get the semivariance. Okay, so that's how this chart here is calculated. So this chart here shows distance. So as distance increases, the semivariance, that's this formula, usually increases. Actually, what usually happens is that it increases to a point where it levels off, particularly in a scenario where we're talking about like level ground. Okay, in areas where we have fairly level ground, as you got further away, you wouldn't expect the points to be all that much different. But as you get really, really close, those points are very similar. Okay, at some point, though, they level off. And we have points that are very similar, but also points that are very different. Whereas if we get close back to the original distance, we only have points that are similar. Okay. And then another input to kriging is the trend. And the trend can be a global trend, or different kriging methods will allow us to also feed it different local trends. Like we can consider the trend on a local basis, which is what this would be doing. Okay, that's a slide I meant to take out. It's really semivariance, but it's calculating it. Showing it in a different manner. I think the other slide was more straightforward. Okay, so remember when I said that when we looked at here, I said that usually we see the semivariance kind of tail off and level out and start to expand. In other words, the values go up and down. We see values that are very similar, but also values that are very different. Whereas here we're only seeing values that are similar. Okay, so that has to do with the shape of the semivariogram that's created. And the points themselves, we refer to that as the empirical semivariogram. And the goal is to fit a model to that empirical semivariogram. And we've got these terms that we'll use: sill, range, nugget. Sill is the value at which no more spatial dependence exists. There's no more autocorrelation. In other words, that variance, that's this value right here. So the value on the x-axis. So the sill can be expressed as a distance. Okay, and it's the value where we no longer see any improved knowledge about our spatial autocorrelation. These values just go up and down. Some of them are very high, some of them are very low, but there's no more pattern in our data out there. That's the point at which the sill occurs. And once we fit a mathematical model to our dots, that is where this line levels off. And after that point, there's really no use. There's no power in using points beyond that distance, that range distance. There's no more points. There's no more point in using those points in our interpolation. So kriging uses that knowledge and says, okay, When I create, when I go to actually make the predictions, I'm not going to use points that are out there because they're beyond the range. Okay, the distance to the sill is the range. The sill, I think I said that wrong. The sill is actually the y value. The range is the x value, the distance. Okay, and then the nugget, which isn't as important as the range, is really the one that tells us, hey, this is the point where we don't want to interpolate past this point. But the nugget is the difference between basically where the this line intersects the y-axis, where it intersects the y-axis. And you'd expect that to be 0. In other words, if points are right next to each other, like 0.00001 away from each other, you'd expect them to be very, very related. But in reality, we rarely have known points that are that close together. Okay? When we're doing interpolation, our points came from maybe weather stations, or our points came from a elevation data set, and there really wasn't any reason to create 2 points that were right next to each other. So we've created points that are nearby each other, and because this is a mathematical model, sometimes this mathematical model will intersect the y-axis somewhere other than 0. Okay. And so that's why that exists. Okay. We can have different shapes, okay, to our semivariogram. The dot here would be the dots would be the empirical semivariogram. The line would be the model that we're trying to fit to this empirical semivariogram. Here, we're going to walk through this, so maybe I won't spend too much time on this slide, but these are the options to the geostatistical analyst in ArcGIS. And you can see that it allows you to see the semivariogram right there. And you can fit different models to it. All right, so here's a few take-home messages. What does it mean? If we've got a noisy semivariogram, that indicates that kriging interpolation is less effective. So we need to use another method or get some more points, because kriging relies on being able to predict the weights through the semivariogram. And so what we're saying, what the semivariogram is saying, if it's really noisy, is that the data is not autocorrelated, and therefore it's not as effective to use geostatistics in order to predict unknown values. Okay? In fact, really all of the methods that we've been talking about rely on nearby values being able to predict other locations. But so if you've got a noisy semivariogram, one option might be to actually create the semivariogram differently. Use a different distance. And we'll get to this in a second, but the distances that are used to calculate these values along the x-axis, you can change that that lag size right here. Okay. In other words, in the example I said all those points that are within 100 meters away, 90 meters away, 80 meters away. In that scenario, my lag distance is 10 meters. So I'm doing 10-meter bins. If you change that, you might see more of a pattern. So if you went every 50 meters, you might see more of a pattern. Or if you went if you got smaller, maybe every 1 meter, you might see more of a pattern. Okay. All right. If the range is large, then long-range variation dominates. If it's small, then the majority variation occurs over short distance. There might even be a trend. If you see a very long range, in other words, see this yellow line as it's going up, and then it bends right about there. Okay, so it looks like the range here is at about 0.6. But if that was a very long distance, you might look at trend in addition to that. But it is true there that if the range is large, long range variation dominates. In other words, the change is very slow. You might be if you deal with like a pollution data set or some elevation probably changes fairly rapidly, or does change very rapidly in relationship to some of these other data sets. Okay, and of course we've said this now several times, but any pair of points beyond the range are not correlated. There's not really any predictive power in using points beyond the range. Okay. So one of the tasks that we have is that once the empirical semi-variogram is created, we get to choose which which mathematical model we use to fit to the empirical semi-variogram. And we can choose a spherical model. These are just some examples. Spherical model means that the range starts close to zero and extends upward almost in a linear fashion until it turns. So we've got a clear range and a clear sill and almost a linear approach to the sill. Exponential. So if we look at our semi-variogram and we see a pattern that looks like this, we want to fit an exponential function. In other words, it goes up, but it goes up in an increasing manner. Okay. Linear, no range in sill. In other words, if let's say we had a data set where it continued out as far as our data set existed, it continued to show patterns of autocorrelation. Okay, very far data was in fact still related, but less related. Then you'd want to do a linear, no clear range in cell. Gaussian looks like this. Okay, the reason they call this Gaussian, another word for Gaussian is a normal distribution. Okay, Gauss was the researcher who promoted this distribution. Okay, so it's a normal distribution. In other words, it's a bell-shaped curve. And if we take a bell-shaped curve and just express it as its probability, going from 0 up to 100, it would look like this. So the bell, you get half the bell, and then you get the other half of the bell because it wouldn't be adding any additional or very little additional towards the end of the function. Okay. All right, so I believe this is where we actually stopped last time. I'm gonna move this. Oh, maybe I'll just kneel on it. Okay, so ordinary kriging is kind of the default. When I say the default, I think it's what comes up when you first select it. But ordinary kriging assumes that the data have a constant mean. In other words, there's no trend to the data. If we were to look at a cross-section, this is a cross-section of the data. So this is the x-coordinate, and this is the measured value. So this might represent precipitation, temperature, elevation. But you could see that the data might have a trend. It might start here and go up and down and up. Okay? And there might be a reason for that. And we might want to fit a trend to that data. But on the other hand, we could say that this data, this trend here was not any real trend. It's just some random variability. So if there's not a reason to assume there's a trend, you don't have to assume there's a trend. If you choose ordinary kriging, you won't be able to choose a trend though. So the only weakness in choosing a trend is if you choose a trend and that trend doesn't really exist, you're gonna have false confidence in your results, your ability to predict. Okay, but this may or may not be a trend. But if we're using ordinary kriging, what we're saying, we're assuming that this data is not trending. It's just random variability. Okay. So here's ordinary kriging inside the geostatistical wizard. And here they've chosen spherical, and the lag size 192. The number of lags are 12. We'll step through this with some actual data here in a second. Okay. You do have the ability to choose different neighborhood types when you're creating your empirical semivariogram. So this has influence on, or sorry, this has influence on the way this will look. Okay. You can choose the number of neighbors to include, and you can also, I don't have a slide on this one, but you can also choose the directionality of that neighborhood. So if for some reason that your autocorrelation only exists in a certain direction, you can actually select that for that particular direction. All right, so this would be the output of the geostatistical wizard showing ordinary Kriging, and this particular chart shows you the blue line here is the predicted value, and then the red dots show you the values that were the input to your model. The dots that were the input to your model. And so you can see that here. We've got our X and our Y and our measured value. Our measured value is, in other words, what the model predicted. Or sorry, what the measured value is the value for the input point. The predicted is what the model predicted for that point. Okay? And you can see the difference between them. And this is what allows us to come up with a confidence or a standard error associated with our data. So this is the difference between the measured and the predicted values. Now, I told you before that Kriging, for the most part, is a predictor that what was the word for that? A predictor that chooses the input values. Remember that? Let's go back here for a second. Remember we talked about different, way back at the beginning of the lecture. It's on this slide right here. Whoops. Exact versus inexact. And I told you that with few exceptions, Kriging is an exact interpolator. In other words, if there is a measured value at a location, it chooses the measured value and uses that, just like IDW does. Trend surface doesn't, but IDW does that. It chooses exact. So how do you reconcile that with, you might be asking, I thought this was an exact interpolator. And what you've done here is said, let me get back to the slide. A few more. What you've done here is said that this is the measured value and this is the predicted value. Those don't look the same. And you're right, they don't. This is a particular output called a cross-validated output. One of the great things about computers nowadays is that we can run something multiple times. And that's exactly what's been done here. And so they call this a cross-validation approach. In other words, what happened is that for every point that was included in this cross-validation, that point was withheld and the interpolation algorithm was run for that data set, and then the value was predicted at that location. And then it was run again with a different point held out. And so when we say the difference between the measured and the predicted value, we're talking about the value at that location and then running the model with that point withheld. Okay. So you can see all these differences between the measured and the predicted values are with that point withheld from the model. So it's an effective tool, not just for interpolation. That's an effective tool for any modeling effort. So anytime you're doing a model in GIS or even outside of GIS, if you have some data and you need to use all of your data to build the model, but you still want to test the effectiveness of the model, you can do something like cross-validation, where you run the model multiple times and you withhold a single value and then test the difference between what the model predicted and reality. When I say reality, I mean the measured value. Okay, that was. Oops, it doesn't matter. I went to the different slide, but that was ordinary kriging, and now we're seeing the output of ordinary kriging. And then one of the things that the cross-validation, one of the powerful things about the cross-validation is we have the ability to output something like this. Okay, and so geostatistical analysis will output something like this that shows the standard error. In other words, it showed the areas where the difference between what was predicted and what was measured were very high using the cross-validation technique. And you could see that for your particular area, we're more confident about the measurements, in these white areas. Those are the values where the standard error is lower than we are in the values where, and it makes sense that those values are higher, the standard error is higher in the periphery because those areas where we have less known points. But then also we have, this area here. And for some reason, maybe there's more variability or it doesn't fit the data as well in that area, and we know that we're less confident about our values at that location. All right. So simple kriging and ordinary kriging are very similar. They have a similar name. The difference between simple kriging and ordinary kriging is that with simple kriging, we assume there's no trend. With ordinary kriging, we assume that there's no trend. But with simple kriging, we assume that the mean of the data is actually known. In other words, we set ourselves what the mean value is, okay? What the average value should be. Obviously, if you don't really know what the known mean value should be, you shouldn't use simple kriging, and that's why it's not used as often. However, if you really did theoretically know the mean value for the data set or you could predict the mean value, then you could use that to do simple kriging. Okay. Simple kriging. There's the standard error. Okay. All right. Now universal kriging. So if we kind of make a diagram of what we talked about so far, we've got ordinary kriging, no trend, unknown mean. Simple kriging, no trend, known mean. Universal kriging, we assume there is a trend, but just like ordinary kriging, or similar to ordinary kriging, the trend function is not known in advance. In other words, we're going to use the data itself to predict what the trend is. So the computer, you feed the computer a trend function, and it tries to fit a curve or a line, depending on whether you're feeding it a polynomial function or a linear function. It tries to fit that line or that line to the data, whether that's a curved line or not. Okay. And in many cases, you can examine your data and visualize if there is a trend. And part of Geostatistical Wizard will allow you to see if there's a trend. And by trend, again, we mean the data is changing through space in a predictable manner. This data probably does have a trend. I mean, you could see that data. Okay? Even this data, even though we used ordinary kriging, there is some sort of trend going on. Okay, it's going up and down, at least, or maybe me going, down and up and down. So it's probably safe to assume that there is a trend there. And so if we do say that there's a trend, it accounts for that, and it's able to make the predictions better. Okay, so here's the screen where we'd explore the trend. So if we look at our data, you can see here we've say there's a first order trend. In other words, there's no first order trend means that it's a linear in nature. There's no bumps in the trend there, and it's basically trending upward in this direction. Okay, trending upward in that direction. So that's universal Kriging. If we use universal Kriging there on this data, you can see that that these are measured and predicted values, and we could compare those to the other models that we created to see if the universal Kriging had in fact produced a better result, and we'll do that with the data that we have. Okay, so we've got universal Kriging, the output there. There's the universal Kriging standard error. You can see that the standard error is lower throughout the data set, except for this area on the side. Okay. All right, indicator Kriging is a special case of Kriging where instead of predicting most of the time with interpolation, we're trying to predict that surface. Well, indicator Kriging, the actual output data is either zeros or ones. Okay. And so what we're trying to do is indicate the probability of exceeding a threshold. So this might be very useful if you were, like, let's say you were in Los Angeles and you were modeling everyday air quality, and you wanted to create a map that showed the areas where you needed to, like, broadcast on the news that this area was going to be very poor. So you set the probability that the air quality was going to be above some threshold, and you did indicator Kriging, and it would show you just zeros and ones. Is the probability that the air quality here is going to be greater than, I don't know what the threshold would be, but is there 90% probability that the threshold is going to be too high, that we need to warn people to stay indoors, to not exercise in those areas, whatnot. That's what indicator Kriging does. And the output looks like this. Okay? The output looks like this. And here's the threshold. The line is just a line because it's just a threshold. It's either you're in or you're out. So the indicator is either 1 or 0. This is what it looks like. So here's indicator Kriging showing you the probability of exceeding a certain threshold. In this case, it was 0.3. So in these areas, it was higher. In these areas, it was lower than that probability. And so that was the output map. We can look at the standard error still of our indicator Kriging predictions. And really, these wouldn't be any different than using ordinary Kriging. Okay, these outputs would be the same. Indicator Kriging is just taking it one more step. Probability Kriging is similar to indicator Kriging, but what you're doing is you're predicting the probabilities rather than in indicator Kriging, you're predicting the probability of being above or below a threshold. In indicator Kriging, you're showing the probabilities of being above or below a certain threshold. So you're really showing very similar data, but the output of indicator Kriging is either 1 or 0, and the output of probability Kriging are probabilities. Okay. So again, with the scenario that I brought up before in Los Angeles, if you wanted to say, okay, the threshold of bad air is X, this output map is the probability that that you've reached the threshold X. So in these areas, you got very low probability that you're at X. In these areas, there's a very high probability, okay, almost approaching 1, that you're going to be above that threshold value. Okay. So the reason why this map and this map look kind of similar is because the threshold that we chose was somewhere in this area, the 0.3 range area. So it's chosen those areas. Okay. And again, your standard error would be similar based on your input parameters. What time is it here? 10:21. Good. Disjunctive Kriging is a nonlinear method, and it basically allows you to consider multiple trend functions within the algorithm. Okay. All right. Co-Kriging is a good cool technique. Okay. Let's say that you're interpolating a surface, and that surface is, well, let's go with a pollution variable again, and it's out in the water, okay, or it's in the air. But you're co-Kriging, you're trying to predict a pollution variable, and you know that it's related to autocorrelation. In other words, nearby values are more related, so that you expect higher pollution in areas where there were other nearby high pollution values. However, there's also some other lurking variable. It could be the strength of the prevailing currents. It could be the strength of the prevailing winds if it was in the air. It could be the distance to nearby mountain ranges. Okay, if there was some other lurking variable that you could use to predict the result, you can use co-Kriging. Co-Kriging allows you to input an additional data set that can be used to determine a trend, or used to determine a that's related to the data that you're utilizing. So co-Kriging more than one variable of interest at a time. Okay. So in addition to looking at autocorrelation, it looks at the correlation between the variables. So if you feed it an additional variable like the prevailing wind currents, it will look at those pairs and see if it can find patterns between those variables. Here's the example that it's giving. You might consider the cross correlation between variables like ozone concentration and particulate matter. Okay, and you actually don't even need to measure these at the exact same locations. All right, so that's co-Kriging. So here's a summary of the options for Kriging. We've got our trend, no trend, that's universal versus ordinary. If trend, what type of trend? You need to choose the trend. Is it a first order, a second order, a third order polynomial? That's what you choose. That's what I mean by trend. You choose the order of the polynomial. Okay. Then when you choose autocorrelation, then when you consider autocorrelation, you get to decide how many points you're going to consider, what the distance is, that's the lag size. The rule of thumb here is to use the average distance between points, or at least start with that. So you can modify the lag distance, but you start with the average distance between points, and by default, geostatistical analysis will do that. You can choose the directionality. Typically, you start off with isotropic first, meaning that, or anisotropic first. You're considering in any direction, but you look at different trends in your data, and if it is that autocorrelation only exists in a certain direction, choose directionality, and then you also can choose the semi-variogram model. Okay, so these are the different things that you can choose, and we'll step through this here in a second. Okay, in fact, maybe instead of doing this slide, we'll just kind of step through this. Yeah, we'll look at some of the Kriging outputs here. So we've got our prediction map. The prediction map is what you'd expect. That's the output of doing interpolation. Okay, every grid cell gives you a predicted value. So Kriging produces this. That's the primary output. Secondary outputs are the standard error map. The standard error map shows you the confidence, how good the predictions are. Okay, and then with the prediction map and the standard error map together, You can do things like create a indicator kriging or probability kriging. Here's a prediction map, and then here's the 95th quantile map. In other words, 95% of the time we'd expect the value to be above this threshold in these areas. Okay, so this would be for that scenario, or be trying to predict air quality. And then we've got quantile maps. We can do probability maps. Okay. And then this is the slide. I guess it used to be table 5.5 in an older version of the book, but this is the slide. And anyway, okay. Let's go to the page. And if you download this thing called example data, we can work through some examples here. Okay. I'm going to save this out. Whoops. Copy, C, temp. New folder. Call geostat, paste it all in there. Okay, so what we're going to do is to open up this this one called semi-variogram model.mxd. And this is just preloading the data for you. Okay, I got to fix that. Probably getting a similar message. On the coast, are you still getting that message when you open up ArcMap?
Yeah.
Okay. All right. I've given David the file, but I know that he had some problems with iTech giving him the privileges to install it down there. I'm gonna close up the table here. So we've got dots that represent temperatures in this case. And here, the data is in Western Europe, but this could be anywhere. This map here, this underlying map, it is just a picture. It's not really GIS data, but it allows you to kind of get your reference, your bearings as to where you are. Okay. You can add data like this whenever you want, right here under the Add Data button. If you choose this little drop down right next to the data set, or right next to the button, you can choose Add Base Map. If you're curious as to how that map gets there, you can add base map data, and this is data that ESRI provides, but it's really just an image. It's kind of like actually, when they started making base maps on the web, they added this functionality into ArcGIS, and it's not. Yeah, there it goes. See, these are different base maps. These are just web base maps that they allow you to throw into ArcMap. You can't analyze this data at all, but sometimes it's good for seeing where your data is. Particularly, what I find it useful for is if you have some data that you don't know what projection it's in, and you try opening up a data set, adding one of these images, and then try adding your data in. And if it doesn't automatically register, then you need to change the projection. All right. Anyway, that's a little side note. So we've got our temperature data of Europe. Okay. And what we want to do is, since this is the first time we've utilized this what do you call it, extension, it may be that this extension isn't even turned on, and some of you may be experiencing this with other extensions because recently you had to log in differently to our computers in both labs. If you ever have an extension that won't turn on or that's giving you an error, in this case you might want to check this. You can go to Customize Extensions and then turn on the extension. Here we have to go ahead and turn on the Geostatistical Analyst. Okay? If we don't turn this on, we can't use it. The nice thing is that once we turn this on, for the computer and the user that you're using, it's always on until you go and turn it off again. Okay? And all this does is our server up here, I don't know how many they have in Golf Park, but our server up here has 100 licenses for this software. So if 100 people had that turned on when they opened up ArcMap, whether or not they were using geostatistical analysis or not, it would be consuming that license. And so we probably don't have 100 machines on campus that even have ArcGIS installed, so we don't have anything to worry about with you just leaving that on. But if you ever went to work somewhere, it might be that you toggle that on and off depending on who in your organization was using geostatistical analyst. All right, but as soon as you close it down, even if you have it checked off, it won't be consuming that license. So it's only 100 concurrent people that are utilizing it. So we did that. Okay. Now, geostatistical analyst has a few tools over here. Okay. But we're going to start off by using today we're going to start off and use the wizard-based version of this extension in ArcGIS. So if you go up to Customize again, and then you select Toolbars, you can turn on the Geostatistical Analyst. I don't know, I have such a hard time saying analyst. Okay, Geostatistical Analyst. So it's on right now. I'm going to go put it up into the toolbar area just so it's not cluttering my screen. So I've got Geostatistical Analyst selected up there. Does everybody have that? Anybody have an issue getting that up to this point? We're all good? Okay. All right, we're going to do some kriging with this data. Okay. So if you go to Geostatistical Analyst, the main thing that you're going to do from this is the Geostatistical Wizard. Okay. There are some other things that you can do. You can subset out some features. Okay. Basically, you can say, I only want to do this area. There's other ways to do that subsetting. You can also kind of examine your data, but the Geostatistical Wizard takes you through examining your data as well. Okay. So that's really the main function. This little button does the exact same thing. Okay. It takes you into this Geostatistical Wizard. See, both of those take you to the same place. Okay. Now the Geostatistical Wizard will actually do both deterministic methods that we talked about earlier and geostatistical methods. Kriging is the principal geostatistical method, really the only one we talked about. Okay, so right now by default it's going to have you select IDW. Okay, that's the default, but we actually want to do kriging. So if you go down here and say kriging, co-kriging, that's what we want to do. Okay. All right. Now, a few things to consider before we continue. One is that this is the data set, and because it's the only data set loaded, ArcGIS has kind of figured out that that's the data set that we want to use. But if you had other point data sets in there, you have to make sure that's the data set that you want to use. Okay. The second one is the data field, and this one is important. I don't know how it knew that temp was the one that we wanted to do. It just did that as the default. We could have wanted to do elevation. Elevation would be a valid data set to do kriging on, but in this example, I want to do temp anyway, and it's chosen that. So I don't know why those are the defaults, but they are. So that's the way that we're going to do that. Okay, so we've got temperatures, we've got temp. The next thing that we're going to do is collect next. Okay, next takes us into this kriging, this main kriging workflow. Okay, we're going to choose. We notice that we have a few choices. We've got ordinary kriging, simple kriging. We've got universal kriging, indicator kriging, probability, and disjunctive, all the ones that we talked about. Okay. For example, we're gonna choose simple, which does mean that we're going to feed it a mean value. Okay. All right. Let's go ahead and I'm looking at my notes here. Let's go ahead and change the transformation type to none. Okay. And the order of trend removal should already be none. Okay. Notice that if you try to click other things, well, this doesn't make a whole lot of sense in simple kriging because there's not a trend. So anyway, it is letting us choose these. I'm not sure what that means, but for this one, the order of trend removal is none because we're using simple kriging. Okay. Then the mean value, we have to feed it a mean value if we're choosing simple kriging. If we're choosing ordinary kriging, there's no trend to give it. There's no mean to give it. We're going to feed it the default mean value. In other words, what it's done is calculated the mean value of the inputs as the mean for the input to the model. Okay. All right. So once we've got this selected, our transformation type is none. Okay. Order of trend removal is none because that's what makes sense. And then the mean value is the only other input. We're going to accept the default and click next. Okay. So here, if you look at this, it's actually started to calculate this this data set. Now, this is not the semi-variogram. This is covariance. This is covariance, but it's still over distance. So in other words, as distance increases, covariance also is decreasing. It's getting bigger and bigger. We're getting more and more variance as we go out, but it's trending down. Okay. The spread is getting bigger. The value is going down, I guess is what I'm trying to say. Okay. As you go out, that's to be expected. You expect nearby points to be more related than far away points. Okay. Okay. So one of the things that we need to do here first is to change under general. Sorry, it's the third one. Variance to semi-variance. Okay. We're going to change covariance to semi-variance so that we actually see semi-variance instead of covariance. We talked more about that in the lab. Okay. In the lecture. So now we see semi-variance instead of covariance. And you can see the same trend happens, but the variance, the semi-variance now is increasing as distance increases, which is what you expect. And you'd see more variability out here. So in other words, points that are very far away are very different from points that are nearby each other. Okay. All right. So choose semi-variance, and then what we're going to do is mess around with the model type. Okay. Model 1. Right now, the model type is stable. We can change it to circular. We can change it to spherical. And it updates. It's not changing a whole lot, actually, but it is changing the nugget and the model slightly when we choose different values here. They're stable again. Okay. Okay, so what we're going to do is change the, I believe the best one, the one that gave me the best predictions was exponential. So change the model type to exponential. Okay, and then oops. Change the model type to K bezel. Spherical. Those are the three that I kind of saw. And look at how it changes this. See how it changed the, if I go back to stable, look at this, the range, that's the range value, and that's in meters. So if I change this to exponential, notice how that's pretty close to the same, actually. Stable, those are pretty close to the same. And then the K bezel, again. So those are the three that I noticed that produced the best one. Let's change the lag size. That's a little bit easier. We can see a little bit more change when we choose the lag size. All right, so let's leave it on K bezel and let's change the number of lags to 10 instead of 12. So move this guy in to 10. Notice how that changes the data a little bit. Okay. Let's change our lag size to something a lot lower, like 30,000. Oops. So look at how when we changed that, we got a much different semi-variogram. See how that pulled that down? Okay. And our range now is 64046 instead of what it was. So the semi-variogram updated. Okay. And then another thing that we can do to change our data is we can update the directionality of our data set. I think that where was that? Let's see, the view, the settings. Oh, anisotropy. Here's where we change it. So anisotropy is set for false. In other words, it is anisotropic. So we could change this to true, and then we would be looking only in a certain direction. See how this changes. So now we're looking more in this direction than we are in the other direction. Okay, let's change that back to false. Okay, I didn't really notice any anisotropy advantage. I mean, any anisotropy in the model. All right. So let's look at the results of our data set. So if we go to next, we can see kind of a visualization of what the output will be. So this is helpful, like if you want to kind of visually see the difference between what something will do. So if we go back here, and let's say we change this back to 60,000, okay, and then we hit next, we can see how different the output's going to be almost in real time, okay, right? And you know, we could, all the time when you're doing interpolation, it becomes very helpful to actually have a feel for how the data should look, to be very familiar with your data. And so if we go back here and change this back to 30,000, the lag size, why would we change the lag size? Well, the lag size is basically helping us to set more and more points along this axis, okay? And to find out what that does is affect this range, and what this range is, in this case, the major range is 64,000. If we went back up to 60, look what the range is. The range becomes very different, very much larger, 600,000, versus if we did 30,000, the range is only, it's an order of magnitude smaller, right? And so what that does is since the range is significantly different, it won't interpolate past that range, and so there's less smoothing that's taken place, and you can see that here. See how there's less smoothing? Okay, the changes are more abrupt, okay. And they're still fairly smooth. I mean, this is European, a full continent's worth of temperature data. Okay. So let's hit next again. And here is the cross-validation screen. It looks a little different than the one that we showed you. It may look different on your screens depending on the version number that you're operating with. But here, we've got the same basic thing. We've got the measured value and the predicted value. And if we look at our errors, our predicted errors, we can see a value here. Here's our mean. Here's our root mean squared error. Okay, our mean standardized error. We can look at these errors. And let's go back here real quick and just change this to 60,000. Okay, hit next, and we look at our errors. And I think let's go back and do it again. 30,000. Our errors actually are increased a little bit. Okay, so with the larger lag size, the default lag size, we had smaller overall errors. Okay. These numbers here, the root mean squared error and the mean standardized error, were smaller. Okay, all right, I'm just going to go ahead and finish this up though. I'm going to hit finish, and if we hit finish and we say OK, it produces the output, the actual output. Now this is still a virtual data set. Okay, this data set will only exist inside of ArcGIS if you hit save. It doesn't actually exist on disk yet. So if you hit save on this and you bring it back up, like if I hit save and I close down this and then I open it back up, it will be there. But it wouldn't be there if I didn't hit save. It's stored only in the brain of the computer. In other words, it creates this interpolation as the ArcMap document opens up. If you wanted to send this to your friend and say, this is the prediction I came up with, then you would right-click on this and say data export to raster to actually save the output data set. Okay. We can, as long as it's what we call a geostatistical layer, we can go look at change output to prediction standard error. So here you've got the standard error prediction. Obviously, where there aren't as many points, your standard error will be higher. This is the error associated with it. Okay. And I thought, nope. I thought there was a way to go back. I thought there was a way to go back to it, but you can look at the method, but it doesn't look like you can recreate it unless you go back through and choose parameters again. Okay. Oops, I chose normal score for transformation type. Okay. So I guess one of the take-home messages here is that there are a wide variety of inputs to kriging. And you can sum them up by looking at this slide here. This slide here. Okay. However, it's one of the powerful things that they've done is created the geostatistical model, and you can use the geostatistical analyst. You can use the geostatistical analyst to play around with your values. We'll do this a little bit more in the lab, but you can look at the error in real time like we did, and we actually built the model that had the higher amount of error. Okay, but there could be a reason for that. I mean, if you're confident in the inputs that you have, and you think that that utilizing those other inputs would be overfitting the model, then you could go ahead and use the inputs that you feel confident in if you're familiar with your data. But these are the things these are the basics that you can change. You can change the kriging type. You can also change how many points are considered. You can do that in a few different ways. One way is to directly do that. Another way is to change the lag size. You can change the directionality. You can change whether or not the semi-variogram model is choosing one with a strong sill or a weak sill that will basically influence the range of what is interpolated or used in your interpolation algorithm. All right. Okay. I think we'll go ahead and end at that point. Does anybody have any questions? Does everybody here? Did everybody here get their tests back? Everybody? I know I still have a few tests. Did you get your tests back? You got it? Okay. All right. We went over the test. All right. So on Wednesday, on Thursday, we'll do a little bit more hands-on with this geostatistical analyst. We'll do some geostatistical analysis with the geostatistical analyst and answer a few questions. This one, this particular lab, we'll use the wizard, and we may end up using the tools a little bit, but we'll mostly be using the wizard. All right. Cool. Well, then now I still have a test from the coast. I don't see him there. Is he there today?
No, he's not.
Okay. All right. I should have left it down there, but I didn't. I guess I'll mail it down to him. All right. I'm gonna go get a drink. Hey, how are you? No, class is over. How you doing? I already asked you that. So, sorry.
Yeah.